Hi, Prakash Mondal. The title of my paper is Predicate Concepts and Their Normal Form. So let's begin with the introduction. Linguistic meaning is such that it primarily rides on the syntax of natural language. That said, it does not mean syntax determines everything that is relevant to the construction of meanings from the meaning-bearing elements of linguistic expressions. That is because there can be certain contextually determined meanings which cannot be fully distilled and so extracted from syntactic relations that are compositional or otherwise. Uh, The purpose of this study is not to show the results of a computational implementation, but rather to show the importance of the concept of meaning relations for AI research, especially in the area of semantic processing, that is heavily dependent on various lexical resources such as wordnet, phrasenet, verbnet, etc. Now, the idea of meaning relations. So the idea this paper advances is fundamentally that meaning relations can be extracted from linguistic constructions, and they do not necessarily have to obey the constraints of syntactic composition, although in certain cases they may, of course, depend on syntactic composition. But then how are meaning relations different from, let's say, predicates or predicate concepts in natural language, such as like, sleep, dance, rain, etc.? The point to be driven home is that predicates or predicate concepts are often coarse grained, whereas meaning relations are more granular because meaning relations often go beyond what is permitted by predicates and their arguments. That means meaning relations involve more objects or items than are permitted by predicates or predicate concepts. Computational systems having predicate concepts can thus be constructed in such a manner that the predicate concepts can be easily coded in terms of meaning relations and vice versa. And this is going to be very important for the current work. Now the difference between meaning relations and syntactic relations. Uh, Not all meaningful associations of linguistic concepts are within the constraints of syntactic composition because certain meaning relations can be compositional in a syntactic sense, and some meaning relations may not be. The notion of syntactic structures, which is relevant to compositionality, is this. Syntactic structures can be conceived of in theory independent terms, in that there could be certain theory invariant properties which characterize syntactic structures. Take, for example, the relation of a verb to its argument, or the relation of a preposition to its complement. This relation can be conceived of independent of whether it is conceptualized in terms of a combinatorial operation such as merge, as in Chomsky's work, or concatenation or unification, as in unification-based formalisms, or functor argument relations, as in categorical grammar, or in terms of dependency relations, as in dependency grammar. An illustrative example can perhaps help us better here. The prepositional phrase over there is in syntactic composition with the noun phrase the waiter in the sentence. The waiter over there looks at my friend in fear and I do not know why. Please note that the prepositional phrase over there may participate in some sort of meaning relation with the noun phrase my friend, although they are not in syntactic composition. The reason is that my friend as an individual can be related to the location denoted or indicated by the prepositional phrase over there. Likewise, the noun phrase the waiter and the prepositional phrase in fear can be conceptually related, as the waiter is in fear or in the state of fear. So in this case, we can construct an agent emotional state relation, although this relation does not ride or depend on syntactic composition. Now, one might argue that it is syntactic ambiguities which provide the right evidence for whether something is a meaning relation or not. So suppose we say that the prepositional phrase in fear is attached to the noun phrase my friend, and in that case the reading would be my friend is in fear. So on this reading, my friend and in fear would participate in syntactic composition. However, on the salient reading of this sentence, the sentence at hand, it is the prepositional phrase in fear which is attached higher to the verb, and this silent reading yields the meaning relation between the waiter and in fear. So here, syntactic ambiguity rather provides evidence for a relation which is not syntactically compositional. Likewise, the waiter and my friend may also be conceptually connected as an experience-experienced pair. Also, the waiter is conceptually associated with at my friend because the waiter as an agent is related to the directional or locative component of the meaning indicated by at my friend. So moving on, we may now want to define meaning relations in more precise terms. So meaning relations can be defined on the set consisting of lex, which is the set of all lexical items, union R1 to RK. R1 and RK are the relations that are subsets of a Cartesian product of lex arbitrary number of times, and this is the primary way in which meaning relations can be defined. However, meaning relations can be defined in other ways too when they are iteratively defined on more and more expansive sets, which is what is shown on this slide. So for example, at first level, we construct some meaning relations on this set consisting of lex union R1 to RK. At the next level, we construct our meaning relations on a more expanded set consisting of lex, once again, union, all relations that are defined on the previous set. And then we can construct further meaning relations on a more expanded set consisting of lex, union, all relations defined on the previous set. So in that way, we can construct more and more meaning relations. Now we may think about some constraints that govern or constrain the definition of meaning relations. So one rule of thumb in defining a constraint or imposing some constraint on meaning relations is to think of meaning relations as filler gap relations. So one example can clarify this better. So our example is a beautifully painted picture of the river. Here, A and picture participate in a meaning relation because A is the gap that requires something which is to be nominally specified, something which is noun-like. And it is picture which is noun-like, and that's why it fills in that role. And it serves as the filler for that particular reason. In contrast, no meaning relation can be formed with A and beautifully because A is a gap and so A is beautifully. Because beautifully requires an adjectival predicate and hence it is a gap. So two gaps cannot participate in a meaning relation, which is what is indicated by the second diagram. Further constraints can also be imposed on meaning relations, and the most important one is the norm reduction condition. So what this condition says is simply that given any arbitrary meaning relation which is asymmetric anyway, if the items X and Y are members of the ordered pair of of the relation concerned, and they can be either the filler and the gap or the gap and the filler. The cardinality of the norm of the meaning relation as a whole is reduced with respect to the cardinality of either the filler or the gap. So in this case, the point is that when you construct a meaning relation, the cardinality of the meaning relation at hand would be reduced related to the cardinality of the set characterizing either the filler or the gap. So this helps us put meaning relations on more solid footing. Now it is time to relate meaning relations to predicates and predicate concepts. And that's why we may talk about now predicates and predicate concepts. Predicates in natural language come in several sorts of adicity. So we can have one-place predicates such as sleep, dance, cup, etc. Two-place predicates such as kill, feel, hold, throw, etc. And three-place predicates such as give, put, hand, etc. Predicate concepts, on the other hand, can be thought of in terms of Jack and Duff's conceptual functions, as in his theory of conceptual semantics. So B is a conceptual function that takes an ordered pair of two items, X and Y, which can be some objects, and then this conceptual function maps that ordered pair to a state. Go is also another conceptual function that takes an ordered pair of object and path and maps it onto a state. To is another conceptual function that takes an object X and maps it onto path. In is a conceptual function for a place which maps an object X to a place. We may now see some examples to see how conceptual functions can be illustrated. So one example is a professor wants a huge library. Here the conceptual function is want, and it requires two objects. One is professor and the other one is library. And library is further specified in terms of its property, which is huge in this case. The second example is Ronnie is in town. In this case, the conceptual function involved is B, which takes an object which is Ron, and then a place which is instantiated by in, which in turn takes an object called town. So this way, conceptual functions are instantiated. So now we may try to establish some sort of equivalence between conceptual functions and predicate logic expressions. One way of doing this is to state what is promulgated in one. So F stands for a conceptual function, and T1, T2 are the terms of the function or the arguments of the function. And equation 1 establishes some sort of equivalence between this and a predicate in natural language, which is P with its terms T1 to Ti. Here the index I represents a variable which is below 3 or equal to 3, because 3 is the upper bound on all natural language predicates. That means take any predicate, it must have a number of arguments which is below 3 or equals 3. And here, what is important to consider is that we are only interested in co-arguments or theta roles of predicates rather than adjuncts. So in that way, we are considering the number of arguments a particular predicate takes. So for instance, if the conceptual function is want and the terms are T1 and T2, it would be equivalent to the natural language predicate want, marked in bold here, and its terms are T1 and T2. So here we have a case of perfect correspondence. However, that may not be the case always. So one example could be the predicate open in natural language. So we can have an example such as I opened the window. So in this case, the CS representation would be cos T1, comma T2, comma B, and then within parenthesis T2, comma open. So this, in plain terms, this roughly means T1 as an agent causes T2 to be in some state which is open. So here, if I open the window, it means I caused the window to be open. Now, importantly, Here, the conceptual functions cos and b have to be normalized to t and t2 because open as a natural language predicate requires only two arguments. So keeping that in mind, we can formulate the equation in two, which says you take any conceptual function with its arguments t1, t2, and so on. It can be written as a functional combination of f with f plus. So f plus denotes as a regular expression one or more conceptual functions. That means you pick up any conceptual function with its terms. It can be written as a combination of one conceptual function with one or more conceptual functions. If that is so, if functional combination f plus will be equivalent to our natural language predicate p with its terms t1 to ti. That is what 3 shows. We may now arrive at a sort of normal form of predicate concepts based on our definition of meaning relations and also predicate concepts. So 4 is exactly what we need to state. So here 4 says that f functional combination f plus, which is equivalent to a natural language predicate p with its terms t1 to ti. So that is that can be written as AMR star concatenation AMR plus. So AMR star as a regular expression means 0 or more meaning relations, whereas AMR plus denotes 1 or more meaning relations. Importantly, AMR star is required for all non-compositional meaning relations in a particular sentence or clause, whereas AMR plus is required for compositional meaning relations. So in a situation, if the value of AMR star is 0, then AMR star concatenation AMR plus would simply be AMR plus. So one example can help understand this better. So if our earlier sentence can be taken as an example, in that case, a professor wants a huge library can be represented as want parenthesis professor, which is definite, comma library, which is not definite, and it has the property huge, and this is equivalent to the natural language predicate want with its corresponding arguments, a professor and a huge library. So it is normalized to AMR3, that means 3 meaning relations, which are non-compositional, concatenation, MR4, 4 meaning relations, which are compositional. So here MR1 is a relation between MR2 and MR3. MR2 is a relation between A and professor. MR3 is a relation between A and MR4. And MR4 is a relation between huge and library. And the non-compositional relations would be MR5, which is between professor and MR3. MR6, which is between professor and MR4, and MR7, which is between professor and library. Here's a diagram which shows the two groups of relations. On the left, you have the compositional relations. So MR1 is a compositional relation constructed out of John and MR2. MR2 is a compositional relation constructed out of things and MR3. And MR3 is in turn constructed out of he and false. On the other hand, the relations enclosed within the dotted box denote all non-compositional relations. So MR4 is constructed out of John and things. MR5 is constructed out of John and false. MR6 is constructed out of John and he. So a simple proof of the normal proof can now be provided, and the only situation where 4 does not hold is when the formulation f functional combination f plus, which is equivalent to a natural language predicate p with its terms, is rewritten as no existent meaning relation. That means this formulation is mapped onto no relevant meaning relation. And if that is so, this is going to be contradictory, given 1, because 1 says, taking you back to the formulation in 1 says take any conceptual function or any combination of conceptual function, it must be equivalent to an instantiation of some natural language predicate. And if that is so, f functional combination f plus, which is equivalent to a natural language predicate p with these terms, must be rewritten as MR1. That means at least one meaning relation. But on the other hand, our initial assumption tells us that a functional combination a plus, which is equivalent to p with its terms, can be rewritten as should be rewritten as MR0. So now this invites a contradiction. Therefore, we conclude that f functional combination f plus, which is equivalent to a natural language predicate p with its terms, must be rewritten as MR star concatenation MR plus. In conclusion, apart from having mathematical implications, this formulation of meaning relations can be very important for natural language processing tasks. So computational systems having predicate concepts from wordnet or verbnet can have semantic representations which can be coded easily in terms of meaning relations. And the ease in conversion of semantic resources in terms of meaning relations does not require heavy resources, precisely because the meaning relations are constructed on the surface structures of sentences. And then meaning relations can also be very important, very relevant for machine translation systems, especially for resource-poor languages, because meaning relations can be easily converted into predicate concepts and back into meaning relations whenever required. And this can help us arrive at certain semantic representations for the job of translation in machines, although we leave it open for further exploration and investigation. So with this, I conclude that the concept of meaning relations can be potentially significant and relevant for different kinds of natural language processing tasks, especially when these tasks do not have to rely on syntactic composition to a large degree, although we leave it open for further research. Thank you.